All right. Hey, class. We're going to be continuing our discussion on gases and talking about some more relationships between pressure, volume, and temperature. Okay. All right. Let's get started on this. Just as a review, go ahead and try and do this quiz on your own. Okay, so the question is, you're camping and someone knocks a can of bug spray into the fire. After a while, the can explodes. Initially the can was at room temperature and 2 atmospheres of pressure. So we can kind of know where we're going this. I kind of like to write down information as I move through because sometimes there's a lot of information in the question. So the initial temperature, so we could say T1 equals 25 degrees Celsius. Since we're doing gas laws, we'll want to eventually convert that into Kelvin. So 25 degrees Celsius is 298 Kelvin. And the pressure is 2 atmospheres. Okay. The final temperature of the gas was 200 degrees Celsius. So I'll say T2 equals 200 Celsius, which would be 473 Kelvin. What was the pressure in the can just before it exploded? Okay, so we don't know what the final pressure is, right? That's what the question's asking. So just writing these out, you can see that we're going to be using an equation that relates pressure and temperature, which we learned in the last lecture is Guy-Lussac's law. And because they're proportional, we have P1 over T1 equals P2 over T2, okay? All right. And I showed how kind of a little derivation of that, I guess, in the last lecture. Okay, so we're solving for P2. So if we rearrange this equation, we would multiply both sides by T2, and we could get T2 times P1 over T1 is going to equal P2. So if our temperatures are in Kelvin, then we can go ahead and just plug this into our calculator and get an answer, right? Okay. So we have you add 273 to get to the Kelvin temperature. Technically it's 273.15, but 273 is close enough. If for most of these you're just going to use 273 because temperature is usually given to you in 25 degrees Celsius or 21 degrees Celsius, and so even if you put the 15 on here, so 273.15, as soon as you add these and then round to significant figures, you're going to have to drop the 0.15 anyway. So generally just leave it off. Okay. Yep, I'm just going to plug those numbers into the equation and solve for the final pressure. Okay. Hopefully that's pretty straightforward. Okay. So we already talked about this one. Pressure is proportional to temperature in Kelvin. So when changing temperature and predicting a final P, we use this, which we can rearrange, right? So I think this is really the important part to remember. You can always just rearrange it using algebra. And if you remember where this came from, I'm going to come back to this a few times in this lecture, but our ideal gas law, which we haven't really talked about yet, is PV equals nRT. This is really all you need to remember. There's going to be like 4 different maybe 5 different gas laws. They all stem from this idea right here. So if we're dealing with a problem where the volume is held constant and the number of moles is held constant, and R is by definition a gas constant, so that one never changes anyway. So we have P and T that change. So like in the problem that we just did, the problem only reported a change in pressure and a change in temperature. It was in like a bug spray can, wouldn't change volume, right? at least once it explodes, it obviously changes volume, but before that, the volume isn't changing because it has rigid walls. And if it's sealed, then gas is neither moving in or out of that container, so N would be constant, so that's the number of moles of gas, and then R is always constant. So if we're doing that, we could rearrange this equation, and we could say P divided by T equals NR divided by V, right? And we could just say NR divided by V because these are all constants, some constant C, right? And then because this is a constant and P over T is proportional, even if we change the pressure, so let's say this is like P1 over T1, if we change the pressure, the temperature is going to have to change with it because they're proportional. So you could say at some other pressure, it's going to give another temperature, all related by this constant. And then if you cut out all this middle stuff, you have this equation here. So again, you may not care about the math derivation. You might choose to just memorize all 5 gas laws, and if this stuff is confusing, don't worry about it. I think it might be helpful for some people though. But if not, just memorize P over T, P1 over T1 equals P2 over T2. Okay, all right. Again, temperature must be Kelvin. That's going to be true for all of the gas equations. Volume must be constant, and N, the number of moles, must be constant as well. Okay, so now we're going to talk about Boyle's law. This relates pressure and volume. So here's an example. Let's say you have this piston and there's some gas underneath. As you push the piston down, the volume goes down, right? But the pressure actually increases because pressure equals force over area. So as you decrease the area, we're pushing the piston down, you're increasing the pressure. So volume and pressure are actually inversely related, okay? So when changing volume and predicting a final P, we use, because they're inversely related this time, it's actually P1 times V1 equals P2 times V2. Again, if we look at the ideal gas law, PV equals nRT. Okay, well, in this equation, gas isn't leaving or coming in, so N is constant. R is always a constant. And the temperature in this scenario, we're going to assume isn't changing if you're just pushing the piston down. So that means that PV equals nRT, right? Or PV equals a constant, because all these are constant. So you can say P1 V1 equals a constant, would equal P2 V2 at some other pressure and volume. And so this is where you get Boyle's law from, okay? And again, you could rearrange it if you want, depending on what you're trying to solve for. And then obviously in this one, temperature and N, like we talked about up here, are constant, right? Because you're only dealing with pressure and volume. All right. So in this example, let's say you have this 4-liter container with a pressure, the gas is exerting a pressure of 1 atmosphere, and then you push the piston down to half of the volume. What's going to happen to the pressure, right? Well, it should double. If the volume goes down by a factor of 2, then the pressure should go up by a factor of 2 because they're inversely related. So we would expect the pressure to double if the volume shrinks by half. Anyway, but regardless, that's kind of a simple example that you could probably do in your head, but you can do it with any numbers using the equation that we have here. All right, so I think I've talked about this before, but I feel like the problem most people have with these is recognizing which gas law to use. So I'm always just going to recommend that as you read out the problem, you write what you know, and if you can see what you know and what the question's asking, then it's gonna be really easy to determine which one to use. And I'll go through that as we go through some practice problems here on the PowerPoint. Okay, if the gas is in a container that can change size, for example, a balloon, right? The container will change its size until the inside pressure equals the external pressure. So this is just an interesting idea that we're going to talk about, but pressure, right, is a force over a certain area. So if the pressure inside the balloon is greater than the pressure outside, it's going to be actually moving out, right? It's going to be expanding. If the pressure on the outside is bigger, then it's going to be pushing down on the balloon, and so the balloon would shrink, okay? Fortunately, I don't have the demo. Okay, and so this is an example of when we would use Boyle's law. Okay, temperature isn't really changing, number of moles isn't changing if it's sealed, but depending on the pressure, we can, on the outside versus the inside of the balloon, it can get bigger and smaller. Okay, that's just a kind of a, I don't know, random, little fun fact for you. Okay, all right, let's try this example. Now, this one, obviously, we know we would use Boyle's law, but I'll still walk you through how I would solve it, even if the problem didn't explicitly say use Boyle's law. Okay, a scuba tank has an internal volume of 11 liters. Okay, so our initial volume is 11 liters, and it's filled with the gas at a pressure, so our initial pressure is going to be 204 atmospheres. Okay. What volume, so we're going to be solving for volume, would this gas occupy if we use it to fill a very large balloon? Assume atmospheric pressure is 1 atmosphere. Okay, so we still need to know what the final pressure is going to be, right, in order to solve this problem. So let's see. Oh, we're going to fill a very large balloon. Okay, so in the last example, we talked about how a balloon is going to fill until the internal pressure equals the external pressure. Once these pressures are equal, the balloon volume will stay constant. So this is basically saying that they're going to take this tank, the scuba tank, and empty, so you have a scuba tank, a little nozzle. You're going to empty the gas out of the scuba tank into the balloon, and it's going to fill up, right? And again, this is going to fill up until the pressure inside the balloon equals the pressure outside the balloon. And the pressure outside the balloon, atmospheric pressure, is 1 atmosphere. And so once the balloon's full, the volume isn't changing. And at that point, we know that the external pressure is equal to the internal pressure. So the final internal pressure of the balloon is going to be 1 atmosphere. Okay, that's how we solve. That's how we get P2. So this one's a little trickier, right? It doesn't just give it to you. Something you'd have to think through the concepts on this one. All right, but at any rate, once you get these 3 numbers, you use an equation with 4 variables, and it's just plug it in, right? So you're going to rearrange this equation to solve for V2. So you divide this side by P2. That's where you get this. Plug in the numbers that we have listed here and solve for the final volume. So 2,240 liters. That'd be a big balloon. Okay. Here's another example. Go ahead and pause this one and try and do this one on your own. Okay. Question says, I place a balloon with a volume of 350 milliliters in the bell jar. It says I place a balloon. This is generally a demo that's done in class. But anyway, we can still do this. Initially at 1 atmosphere. Okay, so there's a balloon in this bell jar, basically, okay? Initially, this is pressure is 1 atmosphere. Okay, and you reduce the pressure until, so this would be the initial pressure, and then you reduce the pressure until the balloon has a volume of 4 liters. What is the final pressure inside the bell jar? Okay, let's go back through this one. So the balloon has an initial volume of 350 milliliters. Okay, so our initial volume is 350 milliliters. Our initial pressure inside the bell jar is 1 atmosphere. Okay, our final volume, the pressure is reduced until the balloon has a volume of 4 liters. What is the final pressure inside the bell jar? Okay. Again, and you can assume the pressure, this is going to reduce until the balloon shrinks down, and then at that point the balloon, after it's shrunk down, isn't going to be changing size. So the pressure inside the bell jar should be equal to the pressure inside the balloon once this is done, right? Okay, so let's see, P2, so we're going to be solving for what's the final pressure here, okay? Again, you got 3 numbers, and you'll be plugging it in. The only thing you have to pay attention to is you always want your units to be constant in these problems. So here we have milliliters and liters. We can't just plug these in to this equation. We have to convert one of these to, we either have to convert this one to liters or this one to milliliters. It doesn't really matter. That would be up to you what you want to do. So in this example, 350 mils is actually converted to 0.35 liters. And then once these are in the same units, then you can plug them in, okay? And get your answer there. Cool. All righty. Charles' law. Okay, so now we're going to be looking at volume and temperature. Okay, so volume is proportional to temperature. And that means as volume increases, temperature would also increase. Again, if you like the derivation idea, for Charles' law, we're just dealing with volume and temperature. So this is going to be an example where pressure and number of moles are constant, and R is always a constant. In that case, we could say pressure over NR equals T over V. All right, so this equals this, which is some constant. We'll say C. Okay, so we're gonna have T1 over V2, or sorry, T1 over V1 equals T2 over V2, right? Oh, or the opposite would be true, I guess, as well. Right? You could have, you could rewrite this whole thing as N over R, or sorry, N times R over P equals V over T. For any of these where it's, V1 over T1 equals V2 over T2, T1 over V1 equals T2 over V2 is also going to be true. So it doesn't really matter. This is probably, I guess, the more conventional way to look at it. So I apologize that I initially said it wrong, but either way would work. Okay. Again, in this one, temperature must be in Kelvin, and then you have pressure and moles that are constant. Okay, so that's what's happening. So I'm hoping you can see that, basically everything revolves around this. It just depends what's constant and what's not, and then you can come up with these like simplified laws basically that exclude everything else if they're held constant. Okay, so go ahead and pause the video, and we haven't talked about Charles' law too much, but I think hopefully using information from the previous ones, you can answer this question. So go ahead and pause it and try this one. Okay, so we're gonna go through this process. It says you place a 750 milliliter balloon filled with helium gas in a bath of liquid nitrogen. So liquid nitrogen is very cold. It's at 77 Kelvin. If the balloon was initially at room temperature, what is the final volume of the balloon? All right. So again, as you go through this problem, just write things down as you move through. So you place a 750 milliliter balloon. Okay, so our initial volume is 750 milliliters, filled with helium gas in a bath of liquid nitrogen. So our initial temperature is 77 Kelvin. If the balloon was initially at room temperature, oh, sorry, messed that up. Let me go back here. All right, let's try this again. You place a 750 milliliter balloon. That is your initial volume. Okay. 750 mils filled with helium gas in a bath of liquid nitrogen. Okay, so at the end, your temperature is going to be, because you're going to put it in this 77 Kelvin liquid nitrogen, and then the balloon is going to go to that temperature. So your final temperature is going to be 77 Kelvin. Okay, sorry about that. If the balloon was initially at room temperature, so your initial temperature is 25 Celsius, which is 298 Kelvin, what is the final volume of the balloon? Okay, all right, so now I got this right. V1 is 750 milliliters, initial temperature is 298 Kelvin, final temperature is 77 Kelvin. You have three numbers. You just need to solve for the final volume. So you can use this equation. Rearrange it to solve for V2. Okay, when you do that, you'll get this. And then it's just plugging in the numbers like we've seen before. All right. All right, let's see. Oh, this is just an example of Charles' law. Okay, so when you heat the air inside of the hot air balloon, right, the volume is going to expand, and the gas is in the balloon, and it's not going to come out the bottom, right? So it's going to stay up in the balloon. So your N is constant, and the density, basically, of the balloon decreases. Okay, so the reason for that is your mass is the same because you have the same amount of gas inside the balloon. So that stays the same, but volume increases because you're heating up the air. So as you increase the volume, since that's in the denominator, that's going to make your density go down, okay? And the same way that, right, you've all kind of been taught, if you have water and you put something less dense than water, it's going to float on the top, right, like an ice cube. If you put something more dense, like a rock, it's going to sink to the bottom. Well, the same is true in air. Okay, if you have air here and something's less dense than air, it's going to be floating up towards the top. Okay, so once the overall density of the balloon, as you increase the volume, is lower than the density of air, the hot air balloon is going to start floating. Okay, and that's why the balloon goes up into the air. So pretty cool application there. I've never ridden in a hot air balloon, but looks fun. Okay, why does volume expand? So higher temperature, right? I think we've kind of looked at drawings about this kind of before, but if your temperature is higher, then your particles are going to be moving faster, right? And so it exerts a greater pressure inside the balloon. Now we talked about Charles' law, how pressure is actually held constant. When you heat the air up, you would assume the pressure would be greater, right? And it is. The particles are moving faster, okay? But the greater pressure inside the balloon actually causes the balloon to expand. And so that pressure actually kind of stays constant, because as it expands, because of the increased pressure, the greater area makes the pressure go back down. I mean, it's happening at the same time. So I don't know if that totally makes sense, but that's kind of what's happening there. All right. So yeah, technically we're dealing with pressure, volume, and temperature, but you can kind of assume pressure is pretty constant because of the increasing area, even though the particles are moving faster. Okay. Charles' law is kind of hard to come up with a lot of examples that actually fit that. Even the hot air balloon, which is a pretty good example, has a few kind of hand-wavy explanations. Anyway, all right, combined gas laws. Now we're going to combine all of the ones we learned. We learned Boyle's law, Charles' law, and Guy-Lussac's law. And so now we're going to combine those together. And really, if we're looking at the ideal gas law, PV equals nRT, okay, we could just say, all right, let's just assume in all cases with all three different laws here, the one thing that was common is that the number of moles were always held constant, right? And R is always constant as well. So those two were always constant in all three of these laws. So let's just say those are constant. Then we can say PV over T equals NR, which is a constant, right? And so then we can say PV and T at a certain point equals a constant, which also equals pressure, volume, and temperature at another point, okay? Awesome. And that's where you come up, after you take out the middle part, you come up with the combined gas law, okay? So you can see these all stem from the same idea, okay? So let's see. Yeah, any two variables can change. We can predict the change in the third variable. So in the last one, we would only change, two variables would change, but we'd have information for 3 of the 4 variables in the equation. In this one, we're going to have information for 5 of the 6 variables, and we'll solve for the last one. As always, temperature is in Kelvin and N is constant in these problems. Okay, so here's kind of a summary. You can take the combined gas law and you can say, okay, well, if temperature is constant, right, cover this up right here on the bottom, then you have P1 V1 equals P2 V2, and that's Boyle's law, right? Let's say pressure, knock the pressure out. If that's staying constant, then we can just kind of knock it out and you get V2 over T2, right, equals V1 over T1 and Charles' law, right? And then the same is true for volume. If you knock out volume, you get Guy-Lussac's law. So you can kind of see that it's they're very similar, very related. The hardest part that people have with kind of this section is just knowing which one to use. And again, I think as you practice more and more, writing down what you have as you work through the problem and what you need is going to identify what which law you're going to use, right? If the problem gives you a P1 and the problem gives you a final pressure, let's say it's Y, and it gives you initial temperature, which is Z, and then it asks what's the final temperature, well, you need something that relates only pressure and temperature, right? So you're going to look for this law here. Or let's say the problem gives you an initial pressure, it gives you an initial volume, it gives you an initial temperature, it gives you a final pressure. This is in some form or another. I guess we'll start using other letters. C gives you a final volume in some other form. D, it says what's the final temperature. Okay, well, you need something with 6 variables. This is going to be the combined gas law that you're going to use, okay? So as you write down what you know and what you don't know, it should kind of clearly show you which law to use, okay? Let's go through this example. You could pause it if you want and try it on your own before I go through it. But here it says a small child accidentally lets go of their balloon, right? Some of us may have done this when we were younger. Okay, now I can already tell, right, in this problem, it gives me a volume, it gives me a temperature, and it gives me a pressure. At this point, I'm already assuming it's going to be the combined gas law because I have all 3 of those variables. But it may not be, but we're going to move on. It floats away. Higher altitudes have both a lower atmospheric pressure and a lower temperature. This is compared to at sea level, right? Pressure is lower and the temperature is lower as you move higher. What will the volume of the balloon be when the pressure is only 0.5 atmospheres and the temperature is 0 degrees Celsius? Okay, so these 3 values are our initial values here, right? The child's holding the balloon that has a volume of 4.0 liters, has a temperature of 298 Kelvin, and has a pressure of 1 atmosphere. Okay, that's our initial pressure. Okay, and then it tells us what will the final volume of the balloon be. Okay, so it's asking for final volume when the pressure, so P2, is 0.5 atmospheres, And the temperature, so T2 is 0 degrees Celsius. That's 273 Kelvin. Okay. All right. So you can see that we need something that relates volume, temperature, and pressure, right? 6 variables. The only one we've learned so far with 6 variables is the ideal gas law. Okay. 2V2, oops, over T2. All right, so we have P1, B1, T1, we have P2, we have T2, we're solving for V2. So once you figure this out, the next tricky part is just reorganizing the equation to solve for V2, right? Reorganized, this would be how you solve for V2. Should be comfortable doing this algebra at this point, hopefully. And then you're plugging all the numbers in and you're getting your answer, okay? It's the same process kind of as we work through these problems. Okay, here's another example. We'll go through this. So rapidly compressing a gas heats it up, right? So if you've kind of learned about diesel engines before, well, let's just talk about a normal engine, okay? So in a normal engine, you have what's called a cylinder, and then you have a piston, right? You might have heard this. Maybe you've seen cars, they talk about pistons. So basically what's happening is, well, that's kind of upside down actually. Sorry, there's probably some car people in the class that are like freaking out. I'm not a car person, but I like to fix dirt bikes, so I know a little bit. Okay, so what's gonna happen is this piston is connected to a rod here, and it moves up, right? As it comes up, it compresses the gas, and then you have a spark plug, which ignites the gas. Okay, there's a little explosion. So the piston moves up, there's a spark, and the piston comes back down, right? And then it lets more gas in, the piston comes up, there's a spark, and the piston comes down. That's a very simple example there. With a diesel engine, what happens is you have a rapidly compressing movement, same kind of idea, right? The piston moves up and it rapidly compresses the gas enough that it actually heats it up to the point that there's another compression basically that shoots the piston back down, okay? In this case, you don't need a spark plug to ignite the compressed gas with diesel. And so that's kind of what this is talking about if you're lost. Yeah, you diesel people are probably going to be like, he said it wrong, but oh well. I kind of know about it. All right. So let's assume the fuel is a gas, right? So fuel is really, I mean, when you get gas at the pump, it's kind of in liquid form. But what it really ignites is the gas form of the gas. That's why it's called gas. Anyway, the piston is 400 milliliters when it's open. Okay, so when the piston is, let's just draw like a cylinder again. When the piston's at its lowest position, okay, we have 400 milliliters of space above the piston, and 18 milliliters when it's shut. Okay, so when the piston moves up to the top, when it's compressing the gas, this space up here, this small space that it forms is 18 milliliters, okay? 18 milliliters when compressed, and that's the compression ratio, okay? The fuel starts out at 25 degrees Celsius and 1 atmosphere. When compressed, the pressure increases to 42 atmospheres. What's the final temperature of the fuel? All right, so now let's start listing out what we know, right? These questions can be a little bit lengthy and hard to digest. Okay, so let's see. The final is this position right here, okay? It's asking the final temperature basically once it's compressed. The initial is basically when the piston is at the bottom of the cylinder. Okay, so at the bottom of the cylinder, our volume is going to be 400 milliliters, right? our initial temperature, yeah, so this fuel starts out at 25 degrees Celsius. That's 298 Kelvin, right? And it starts out with a pressure of 1 atmosphere. When compressed, the pressure increases to 42 atmospheres, okay? And also when compressed, the final volume is going to be 18 milliliters. Okay, the question is asking us what is the final temperature, so this is our unknown. And the final pressure it gives us is 42 atmospheres. Okay, so you can see there's 6 different variables and we're solving for one relating volume, temperature, and pressure. So this is going to have to be the ideal gas law. You're going to solve for T2. Okay, so rearrange the equation to solve for T2. And then you're plugging in the numbers and getting your answer. So the gas temperature increases to 563 Kelvin. Okay. All right. 290 degrees Celsius. Okay. Auto ignition temperature. So this is the temperature, I believe, at which diesel would auto ignite on its own, meaning that it, like how we talked about before, it wouldn't need a spark plug to ignite. Just that compression brings the diesel high enough to a high enough temperature that it ignites itself. It doesn't need spark plugs. Okay. All right, cool. I believe that's also, somebody may correct me, why diesel engines have a hard time starting in the winter, right? Because since they don't use spark plugs, they're relying on temperature only to ignite the diesel. So that's, you may see like a plug hanging out of the front of a diesel truck. They plug them in at night if you live in a cold place to keep the, there's like a heater that keeps the engine warm. So when you go to start it, it's warm enough to actually start the engine, right? If it's too cold, it wouldn't reach a high enough temperature. Because if this is saying the fuel starts out at 25 degrees Celsius, but you know, if you live in Rexburg, like where I went to school up in Idaho, and you know, we'd wake up in the winter and it was like negative 20 sometimes, negative 20 degrees Fahrenheit, but then which I think is actually like, don't quote me on this, I think it's like negative 40 degrees Celsius or something like that. Then your temperature change, right? This goes from 25 degrees Celsius to 290. Well, it wouldn't be, a change wouldn't bring it up above 257 degrees Celsius. So it wouldn't bring it high enough to actually ignite the diesel and start the engine. So that's what the heaters are for, and the little plugs you see hanging out of the diesel trucks. Anyway, pretty cool stuff. I think it's really interesting. Okay, that's the end there. So we learned some cool real-life applications, hot air ballooning and diesel trucking. So anyway, biggest things I'm hoping you can pull from this lecture is we talked about 4 different gas laws. So you need to know those 4 laws. You can either just memorize each one if that's easier for you, or you can derive it from the ideal gas equation, which is PV equals nRT. And I believe on the equation sheet on the exam, it only has PV equals nRT. But you should use these enough that you'll probably just have them in your head anyway. Anyway, knowing how to like work through those problems and solve it, the homework would be a lot of help. It's going to have some problems similar to this, where you're using these gas laws to solve for final volume or final temperature and stuff like that. So, all right, that's going to be it for this lecture. Have a great day.